Okay, cool. We'll get started now. So I'm Chris. I'm the CTO at Leap Year Technologies. Leap Year Technologies is a data security company in Berkeley. And primarily we're working in the intersection of cryptography and machine learning to provide certain data security guarantees for our software. And so the talk today is coming out of my experience working on this project, on some of the tools. I've got some code that is a simplified sort of version of what we've done. But really, the foundational thing that we've wanted to do is provide static type assurances at runtime. So to prevent mistakes starting from compilation. And so my goal today is to introduce you to some tools that we found useful to do this. Now, I just saw Sandy McGuire walk in, but I just was at his talk, and sorry to plug you here, but his talk is on some overlapping subjects. It was very good, and so if you guys were there, hopefully this will augment that work. But I want to show some of those tools and some additional tools from the Haskell ecosystem that can give you help you in constructing various interfaces to your libraries out there or APIs out there. So the topic today is statically typed interpreters, and we'll definitely be going through the development of a small statically typed interpreter in Haskell. But more importantly, I want to emphasize what these tools can do for you and the generality of these tools that hopefully can help you provide better guarantees on your interfaces as you start to develop. So this talk is going to be very straightforward today. First, I want to talk a little bit about the motivating problem that we experienced at Leap Year. And then I want to go through the actual process of developing the statically typed interpreter, going over the three primary tools that we'll be going into. And then hopefully I'll cover a little bit of general use cases, highlight ways in which I've seen these tools used, and ways in which I imagine these tools could be used further. So the core problem that we had to solve at Leap Year with regards to this presentation is how do we give a user an interface where they can structure arbitrary queries, which are essentially programs, in a SQL-like language, and prevent them from doing bad things, and also, with respect to our privacy mechanisms, also guarantee that those privacy mechanisms are functioning correctly. And so we really had to implement a relational algebra engine from the ground up. Luckily, we're not stuck on the SQL 92 standard or any of the other versions of SQL that are out there. They're kind of crufty, honestly. And so we were able to really just hone in on relational models and relational algebra. But there's a larger problem, really. Is how do you implement these large interpreters? And there's lots of moving parts. There's lots of things that could go wrong from the development perspective, and there's lots of things that the user interacting with this interpreter could do, and they might not understand what's going on with the errors that you make, or errors that you return to them, or the lack thereof. So if anyone has tried to implement a strongly typed or statically typed SQL, or even has tried to implement an interpreter, they'll understand what a problem this can be. So today, I'm going to go over a simplified expression execution engine, which is given pretty much by that type signature, eval. So we want to take in a string, and we want to produce, did I go past that? A result type, yes, I'm sorry. And for today, it'll be IO. So we'll just print the result to the screen. And so hopefully you're not using string, actually, you're using text, but that's a little bit besides the point. So the tools we'll be going over to solve this problem today is first, we'll be looking at some of the language extensions that are available, GADTs, first and foremost, along with existential types and data kinds. And then we'll be going into the data constraints module from the constraints package, something that's been indispensable. And finally, if you have this, compiler's knowledge will be incredibly helpful today, but not required in any way. I'll try and go into as much detail as is needed to understand. But it'll definitely be very helpful in terms of understanding what's going on under the hood. So let's dive in. the first thing that we need to do really is some parsing. So we have our basic language here. So in our language, at the top level expression, we have a literal type which will encode any kind of basic values that we might need. Today, we're restricting ourselves to strings, integers, and doubles. Additionally, there's a variable type which we use to allow bindings paired with, as you see, second from the bottom, the let binding. We'll also have binary and unary operators. We've separated them for ease, and I think it'll be clear why later when we get to some of the more strongly typed semantics. And then finally, we have a basic conditional if then else. So it's not super complicated, but this should be enough to get us to show off all the tools that we're going to be working with today. So a little bit more about the language. The binary operators which we'll address are the basic arithmetic operators, some logical operators. Our unops are going to be negation and absolute value. Our values that we actually encoded, as you mentioned, are only one of those three. Did I say string before? I meant bool. So here's just a simple program of sorts, is an expression here. So we have one let binding, one conditional, some comparator operators, and some literal values. And on the right, we have that same thing translated into our language. Now, it seems like we're on the right path to do everything we need to do. You can see that we can encode, anything that we really wanted to within our language here. But there is a problem. Now, the problem is these examples here, and a bunch of other ones. The problem is that we can't produce any guarantees about when these are constructed, about their types. So here we have an example where we are trying to add a Boolean to a literal int. And we could potentially do that like C would, but it's not going to produce the right behavior that the user would like. It won't make any sense to the user, especially in some more complicated scenarios. And so what we want to do is we want to be able to encode this in a more type-specific way. So that if we ever run into a problem actually encoding this in this more type-specific way, we can let the user know what the error is at the spot. So what we'll be doing is we'll be introducing GADTs. So we can, as you saw, we can reprimand semantically incorrect programs. But we can correct that. We can prevent that from happening with GADTs. So the first thing that we'll need to do is we'll actually have to introduce our typed version of the AST with GADTs. And then we'll have to use constraints to do some proving about some additional properties in our ADT or GADT. And we'll be going over that with the proof functions. So in our language, this is what the typed GADT version looks like. So if you're not familiar with GADTs, this is a great chance to learn. GADTs provide us a lot more semantic flexibility and a lot more precision in what we're doing, fundamentally. So as you can see, we have a bunch of constructors defined. These look a lot like functions, as you should really think about constructors in general for ADTs as. In the first case, we've got a literal, which will take in some value of type and produce a typed expression of type, or ty. The variable will take a string and produce a typed expression of ty. So these can really be anything. They're unbound. But as you'll see with the bin op, this is a little bit more complicated. We'll first put in a bin op that has a type in and a type out specified. And this specifies for us in the GADT the typed expression of type in for the left-hand and the right-hand side. And then it will also give us something, a typed expression of tie out. So that I'll try and make that a little bit more clear as we go along through the slides about how the type specificity work. It's probably not clear here, but it would be clear once we introduce these things. So our bin ops, what we do to construct our bin ops, for the equivalent representation is we will, well, for the bin ops, we're actually going to specify constraints on our types rather than specifying the types themselves. But there's also the logical operators, which are restricted strictly to the Boolean type. So as you can see, our tie-in and our tie-out as type variables get bound to this specific type. And then going back over here, we can see that binop is thus bound to a concrete type. Similarly, the unops. We're also going to need another little bit here with GADTs. So we want to have some type markers, essentially, is what you should think about these as. And so we'll either mark something with value level bool, value level int, or value level double constructors. Try not to confuse them. They are kind of confusing, but but yeah, they essentially specify concretely what the type of the expression should be. So let's let's look at some translations here. So this is the prior expression that we have. So we will take and we will show that the let is yes. Let me just mirror my screen. I'm having a hard time reading this. So we have the example from previously. We have let a equals 2 times 3 and if a greater than 0, then a else 0. So we'll first translate this to the untyped version. And then I will start to pull out all the individual pieces and show you how the typing works for this particular example. So in the first case, we have this binop, which we're going to be assigning to A. So the binop is taking a literal of value 2 and a literal of value 3, both type int, and is taking a mul, which, if you recall, was restricted to the num class, but fortunately int satisfy the num class, and overall, when we construct this value, we end up with a typed expression of type expression int. Similarly, we can go through the multiply here. Oh, this is breaking it down a little bit. So this is just breaking it down a little bit further. Here I specified that the num x is actually a num int. And we just construct that, and that's how you get the typed expression of typed int. And then we want to move on to the bigger thing. So we know that we've assigned it a type int, so now we can say that variable a is of type int. And there's some scoping issues with that we'll address later. And then what we'll want to do is we'll want to, for the predicate check in the if then else, we'll want to construct a typed expression of type bool. Fortunately, we will check this variable a, which we previously referenced, compare it with 0, and get a binop of type bool. Then the if then else can be constructed actually by putting all these things in. So we'll get our predicate, put it in, either we'll return our variable if the predicate is true, which it should be, and otherwise we will return, the value 0. So there's another little piece that we need here. Going back, I mentioned that we have this GADT called type, and so we're going to use a pairing constructor here, which I've tried to model kind of like : which is a type annotation, but it's just an arbitrary pairing operator. Pairing over not necessarily functors, wrapper types, I guess if you want to call them that. And then we'll create an alias that's a typed expression of typed x, which essentially means that we have the expression itself as a typed GADT, and we have the type information tagging that typed expression. The last big component we need is we need some components that will, or some functions that will actually translate our ADT representation, which doesn't have the type information, into this typed version. And so let's just run through an example here. I want to highlight an issue that we run into with this. So The first thing is if you remember the unop is specified either at num for the negation operation, or it's specified at boolean for the not operation. And so if we were to take in an expression, we were to match unop here as our binary operator, we would see that we'll get a unop, and then we'll go check that the unop and the two expressions actually match what the output type should be. And so we will then check that unop itself for what it ought to be in terms of the intended output. Unfortunately, because the two arms actually are type specified at different types, the compiler will complain that it can't match the first type with type bool. And so there's something a little inconsistent about the way that we're outputting types. So what we need to do is we need to introduce existentials to get around this problem. Essentially, we have to tell the compiler, no, you don't need to care about this type information. I've got this under control, and I will solve this a little bit later down the line. And so what we have here is we have a constructor I like to call A, because it is semantically kind of like the article A in the English language. And what it takes in is it takes in this type wrapper F, which for our intent purposes will either be a typed expression or a t-expr. And what it essentially does is it quantifies over all the potential types that could be fixed at to erase that information and say that it's merely a typed expression. With a little bit more machinery, this is just a sneak peek into like some of the things that we've developed at Leap Year. We've got this more full-fledged version, which is takes also a constraint. And so what it allows you to do is it allows you to, after taking things out of this A, reference that constraint later. So if it was a num, you might be able to, or you might want to access multiplication or addition. And in that way, you don't have to reconstruct what the type is. You'll see that reconstructing the types for the compiler is a little bit of a problem that we'll get to. But another thing this is good for is custom type classes. So if you want to carry around custom type classes and not have to, again, reference the concrete type, this will allow you to carry around the extra information. So we can rewrite our check expression function in terms of this A. And now what we're saying is that we don't care about the type specificity, at least at this moment. We just get a typed expression out. So if you recall, some of our GADTs had constraints on them rather than typed specific concrete types that we wanted. So this is where the data.constraints library comes in, or constraints library. So a constraint is, or the dict is the fundamental tool of the constraints package. And it's a little bit of some compiler wizardry, so to speak. But here's its definition right here. And so what it does is it says that we have for a particular type, a particular constraint that satisfies that type. Some way, or a way you can think about this is in more object-oriented languages, there is the idea in compilers of a v table or a function table or a method table out there. And so you need a reference to that table to actually access the functions for that particular class, especially if you're doing subclassing. And so this is a very similar way. This produces essentially a reference to that table of functions so that we can access them later, even if we don't know what the type is. So one thing that we needed to do before was for our multiplication types or addition types, we needed to know that it was a num. So we will have to produce dictionaries which provide access to that function. And so when we're actually checking those particular binops, we need this check num instance. And so all we need to do is put that type tag that we had in there previously, which is specifies a concrete type. And it will tell us whether or not, in this case, we have a dict for that because bools don't satisfy num. It'll tell us if we have a dict for that, and then we can later make reference to that. So the last piece that we really need is we need scoping. So scoping is rather simple, but it gets a little bit hairy actually, because again, for this extra type variable that we had floating around, we can't construct a map that's both string to type bool and type int, but we can elide that type information using the constructor and access that. So when we're actually going through the type checking process, we're actually able to reference that information. Now, now that we've gotten through all the pieces that we need to actually get up to the stage of building a fully typed AST for our language, we can actually now evaluate the AST. And we've done pretty much all of the work up front for that. We have all of the reference dictionaries we need. We know all the type information. There's no invalid expressions contained within this. And so it becomes very simple just to deconstruct this and to evaluate all of the binary or unary operators that we would need on this. So the first piece that we need, though, is the base case. The base case is a value. So what this will do is this will unwrap a value to actually get the type out, or the value out, according to the type. And then once we get over to the binary operators, it becomes quite simple to actually evaluate, because we just have to evaluate each sub-expression and then use the respective operator that we needed paired, that's the sister or brother of the constructor that we needed. So for and for multiply. Some of the things that I think that are useful for actually taking away from this in terms of building interfaces and APIs for other developers to use or for end users to use. We have a great example of existentials in the HDBC package. So this is a kind of old package, but let's actually write it out if I remember. Okay, so there's this data type called conwrapper. And what it does is it uses a for all con such that connection. I forget what the actual class is in this library, but it's essentially provides the all of the things that you actually need to do to interface with a ODBC compliant database. And this gives you a conwrapper of the con. So what this is doing is this is aligning some type information for the particular connection that we have, which might be a Postgres instance or some arbitrary ODBC driver. And instead, when you're calling into the HDBC library, it will unwrap this, and because of this existential constraint, but the existential paired with the constraint, we know that there is some implementation or instance of the connection for this, but we don't need to know the particular type of the connection or anything like that. So the library is flexible in that way. A great place in which I've seen the data constraints used quite a bit is the Sparkle library. So if anyone here is familiar with Spark, these guys at Twig wrote a really awesome library that connects into the Spark ecosystem. But sometimes you want to work with polymorphic types, and so you usually need some constraint on that. Maybe it's only num, or maybe you need some special type class. And so data that constraints comes in handy because along with static pointers, it allows you to reference explicitly all of those instances as you serialize your data across to the individual nodes of your Hadoop cluster. And again, any kind of parsed examples similar to the interpreter today are very helpful. So if you're working with some kind of servant API or anything that's user-facing, you can take somewhat structured AST representations, and then you can translate them into a more constrained version of your language, which gets you all the things that you need for free later when you actually want to execute or do something with respect to that query. And so that actually concludes today's talk. So I'm open for questions. I'm sure I missed a few things here and there.
I noticed on the initial check you had expression going to type expression.
Yes.
Surely an ill-typed expression, you can't get back to that?
An ill-typed expression, so you can uncheck the expression. So if you want to look at it in mathematical terms, we have, let's say that we have two sets, A and B, or I'll call it U and T, untyped and typed. And so what the checking function does is it provides a map between the untyped and the typed. But we could definitely uncheck it because in some sense there is a subset of T, let's call it small t, subset of T. No, subset of U, sorry, which is isomorphic to T.
Yeah, of course.
Yeah.
What I mean, what I can't understand how this could be properly typed if I could pass and if one then whatever into this. Isn't this promising me a typed expression back? I would have expected an either or a maybe or something.
Oh yeah, I'm sorry. So there's a little bit of incorrectness. You're right here about the code. So that bit is elided. If you look at the coding example, you'll actually see that we use except as our thing for throwing errors. So I didn't actually talk about how to throw good user errors. I think that's another little bit of presentation in and of itself. But
Is that relational algebra level you came up from open source?
Is it what?
Is it open source level? Is it relational algebra level?
No, it's unfortunately not open source. It's still quite heavily under development. It might be someday, but at this point, development is a little bit too quick to do something like that.
Do you use parsers or do you mostly work with EDSLs?
We work with both. So we provide an interface directly into a SQLite language for typing your queries. Unfortunately, a lot of the things that you'd like to do in data science and machine learning are a little bit too complicated to simply do that. So they lend themselves to more programmatic interfaces. And so in that way, we also allow construction of the EDSL directly. Well, indirectly through JSON, but.
So if you deal with EDSLs, do you also use let terms explicitly, or do you?
So I introduced lets for the purposes of today. We actually don't do any kind of the semantics of variable binding and relational algebra are a little bit different. They have to do with the way you might do projections from a source table or a source data, and the way you would recombine that. Because essentially your variable usually represents a column instead of a single value. But yeah, back to the point, the let binding was primarily introduced for the purposes of today. There's a lot of headaches that you have to solve in terms of SQL with heterogeneously typed data structures.
Was there any reason that you use data instead of new type for never use for all and various?
Oh, the A? Is there a reason there?
I didn't know if maybe that kind of quantification that you're doing, like prevented you from being able to do new type for some reason?
No, I don't think so. I think it might be with the additional constraint you have to use data to construct that. But for the plain old A, actually, you can construct that with just new type. Actually, no, I take that back. If you do have constraints, you can also use a new type.
You can use a new type for some types because they have different runtime notification.
Wait, you said you can or can't?
Because if you can pass a constraint, there's next runtime dictionary attached to it.
You're right. Yeah.
Have you tried like embedding things like maybe like some polymorphic like higher kind of type into this?
Yeah, so one of the things that it's actually really hard. We haven't found a kosher way to do that, but yeah, when you're actually handling nullability, that becomes a very big issue. We've actually found that it's easier to introduce a null tag rather than to use maybe as your type, because you run into a lot of headaches.
Yeah, I run into similar issues trying to good solution.
Yeah. Well, one other thing is that we also do this special type family thing called representations, where we essentially condense the data down to a representation. And so we kind of get nullsif free through that by having a special null rep that can't be accessed by other data types.
Do you do transformations on AST?
What's that?
Do you do transformation or optimizations on the abstract syntax tree?
Yes, we do. We do a few.
If you have GADTs with type, then doesn't make it too complicated
To do that?
to express the transformation.
It.
Because we have to prove that it doesn't change the type.
That's an interesting question. I really don't know the answer to that because we haven't done any much more than basic transformations.
Information on untyped and type checking.
Yeah, you could. Actually, type checking is quite cheap, so that effect is a utilitarian option. It is quite possible. Cool. Well, thank you everyone for showing up.